what if you had something which was non-linear? And there are some special ones we'll look at, special equations which we can modify to be solved using the tools we've developed so far, linear regression. So this last part is third part. I'll call it tips for linearizing nonlinear functions. Okay, there are special forms of equations which can be reduced to a linear regression problem. So that's convenient because once it's linear, you can use linear regression formula, which we derived earlier. Okay. So what are these equations? Some of these equations are of this form. If you have y equals a times e raised to b of x, and you say, wow, that is so complex. How can I even curve fit a and b using that? Turns out that this is actually very simple. This is why it is simple. So we'll take logs of both sides. So log y equals log of a, and you can take log to any base, doesn't matter. Well, sorry, you need to take log to the base e. Okay, the reason is because there's an e here. Take log. When I say log here, it means log to the base e, because if you take log to the base e of e, so log e raised to bx, this thing actually boils down to bx, right? This is actually e here. That's what log to the base e means. So when you have e, it's always bx. Okay, so now that we have, let me write this, call this z, okay? Let's call this a bar. Okay, just a new name. But now we can write this as z equals a bar plus bx. So this is the crux of it, which is you started off with a non-linear formula. This one looks very complex, but by taking logs, you've reduced it to a linear equation z equals a plus bx. Now once you have a linear equation, you are ready to use the tools from linear regression to solve it. The formula which we wrote for linear regression was over here. If f equals ax plus b, then you can write analytical formula for a and b, right? You just have to use this. Simple as that. Once you fit a and b, so what you'll do for this is you have x and y, right? That's your data. You'll be given the data. Now what you'll do is you create another column, z equals log ey. How will you do that? You'll take this y, you'll take the log of that to the base e, and you'll get z. So create this column for yourself. And that's that. So once you create this column, fill this dots. It's basically you just take log ey, and you're ready to use linear regression formula to solve for, now you'll get a bar and b, right? B is straightforward, you know what. But when you get a bar, you're not interested in a bar, you're interested in a. So you can see that a bar is log ea, right? Which means that a is exponential of a bar. So you will compute a bar using linear regression. Then you'll find what actual a is by using this formula. So you're going to go to reverse substitute. Okay, so that's basically the trick to simplifying these equations so that you can use linear regression. And I'll solve one problem so you get the hang of it. And then you'll do one more for the homework. Yeah, now you could use the same method for something like this. Okay, so you could just take log, doesn't really matter which log of what. So for example, log y equals a plus b log x. Okay, so then what you'll do is you'll call this as z. You'll call this as, well, not this. This as, let's call it x bar. And then you have z equals a plus b x bar. Then you generate a table with x, y, x bar, z. Fit a and b, and you've got the answer, right? So that log really can be any log, can be log 10, log e, whatever you like. Okay, so this is one way. That is, if you have a term which has an exponent, x raised to e raised to, use this trick. Take logs. That's one way to do it. Another way this can manifest is this. Suppose you have an expression like this. Y equals c1 plus c2 plus x. Okay, this looks complex too. In fact, you have 1 divided by x. So there's no way, feels like there's no way you could fit this with linear regression, but there is actually a way to do it. What you can do is move things around. So I'll move, or I'll multiply both sides by c1 plus x divided by y. So when I do that, c1 plus x times y equals c1 plus x divided by y times c1, c2, oh my god, it should be c2 plus x, not c1. So what you observe is that this cancels off, this cancels off, and you're left with c2 plus x equals c1 divided by y. Now what you can do is the following. You could just call this as z. Wait, hold on, it's not in standard form. We'll actually divide. We don't want to have anything on the right side, so we will divide by c1. So we'll get c2 divided by c1, 1 divided by c1 times x equals 1 divided by y. And this is where you use linear regression. Let's call this b. Let's call this a. That is a. And let's call this z. So you have z equals b plus ax. And now you can do linear regression. So what you'll do is you'll create a table like this, x, y, 1 divided by y. This will be a z. And then proceed, compute a and b, and you'll be done. Okay, one more form you can do, and I'll just put it down, but I'll not dig into it. Similar method can be used for y equals c1 plus c2x. Okay, so you can just take the 1 divided by x and make a x bar, for example, and then you have a plus bx. Okay, but the main thing is I want you to apply this. Let's solve a problem where you do this. It's easier shown by doing an example problem. So let's do a problem. So here is some data, and the problem is fit the equation y equals a times e raised to bx to the data shown on the right. Okay, so what we did here was we take logs of both sides. Log a y equals log of a plus bx. So log, and the log is to the base e. So when I do log of e raised to bx, it's just bx. Let's call this z. Let's call this a bar, and this is bx as is. Okay, so next is there's a formula for a bar. The formula is something like this. Xi zi xi minus xi square zi. Okay, so where did I get this formula from? This is taken from linear regression. It's this formula, just that I replaced y with z. And then there's a formula for b. It is summation xi summation zi minus n summation xi zi divided by okay, so then we ask ourselves what exactly is needed to compute a bar and b. You can see we need xi zi, the product. We need summation of xi. We need summation of xi square, summation zi. This is already computed. Xi square is also computed. Okay. So what I would do is I'll make a table containing these columns. That's way it's easiest to do it. So note that z is log of y. So this is what you'll do. You will make a table x z equals log y, then x square x times z. Okay, and you'll populate it. Okay, so what I did was, just to save some time, I'm running out of time. I'm just going to, I did this in Octave, but you can do it in Octave, but in the exam you need to do it by hand. This is what I got. Okay, so I actually don't need y, so I really didn't write it down, but x z is log of y, x square x z. Once you have that, you can, you'll actually need to sum this up. So you need to write the sum of this. This will be summation of z. You have to sum this. This will be summation of x square, and you sum this, you get summation of x z, and then when you sum this, you get summation of x. Okay, so I don't think I wrote this down, but it's just a matter of summing all this, and whatever comes here, sum, will go in right here in A bar and B, and everything is here. N is, by the way, 11. There are 11 terms. You can count these are 11 data points. So is 11. Okay, so doing that, you get if you do this, you get from the previous page, A bar comes out to be minus 0.6409, 6407, sorry, and then B is 0.9794. And then remember that we are after not after A, but after A bar, but after A. So A bar and A are related. So we have A bar equals log e to the base A. So A is e raised to A bar, which is e raised to minus 0.6407, which is 0.5270. So we have, in fact, found what A and B is. We were after A and B. Is here. So our fit is y equals A e raised to bx, which is 0.5270 e raised to 0.9794x. Okay, and then let me just put down the plot. It's always a good idea once you get the fit to plot the data, because you may be wrong in the fit, right? The data points, the solution might be wrong. So I'll just insert that and we're done. So this is what I got for the fit. The blue dots are the data, and then the red is the fit.